Today, exam 4 is due on acids and bases, and we're going to start a new topic for that will be covered in exam 5. So I'll begin as usual by sharing the PowerPoints. And there we go. Now let's make a slideshow. There we go. Now I think I'll minimize this one. Yeah, that's better. I can see the whole thing. Okay, chapter 16 in your book covers two topics. Solubility, that is, solids going into solution, and complex ions. Now, on the surface, these two topics might seem unrelated, but they are both related in terms of how to increase solubility. We discuss ways to increase solubility of solids that are sparingly soluble. Well, in the past, let's put it that way. In the past, we've treated solubility as if it's black and white. A solid is either soluble or insoluble. Fact of the matter is, solubility is on a continuum. And you have to arbitrarily decide at some point what to call insoluble and what to call soluble. But the topics that we're going to cover in chapter 16 approach solubility from an equilibrium standpoint. So, and you'll recognize, I hope, that every solid is soluble to a limited extent. So rather than burning up airtime with discussions, let's move to this first slide. Pardon me for a second here. There we go. Okay, solubility. Remember when I first introduced the topic of the K values in equilibrium? Right? We had products over reactants. But I also pointed out that these K values could have subscripts. And some of the subscripts were reserved with special meaning, like KW is for the equilibrium constant for the dissociation of water, or KP refers to the equilibrium constant when the expression is in terms of pressure, gas pressures. There are others. Sometimes we say KEQ to denote just a general molarity-based equilibrium constant. But there's one that we're going to introduce today, the KSP. Which is the designation for K values for solids and their solubility in aqueous solutions. Now I say aqueous because that's predominantly what we're talking about. We're going to focus on aqueous. You can devise Ks for solids soluble in other solvents, but we don't have time for that, and most of the solubility concerns are in aqueous solution anyway. So what do we call a solubility product? Well, look at this example, right? Bismuth sulfide. Sulfur is a 2- charge, bismuth is 3+ charge. So you have 2 bismuths and 3 sulfurs in the solid form. That's a crystal lattice. And these are all crystalline solids. They're all ionic compounds that we're discussing here. So what can happen to that? Well, if we put it in water, then you would expect for the ions to break apart into cations and anions. And based on the formula, you should have 3 sulfides and 2 bismuth ions. So that's the balanced equation. If we write the K value for that, products over reactants, notice that the product is always a solid. And the convention in writing K values is solids are not included. Well, neither are pure liquids either, but we don't have any pure liquids here to deal with, just the solid. So notice that in a K expression for solubility, it's always the product of products. The product of products. The product, in chemical terms, are multiplied together, which is the product in mathematical terms. So that's why we call it the solubility product, because it's simply one multiplied by the other. And of course, don't forget the powers. These coefficients are important, essential. Okay, so that's the way you express a solubility product for a reaction. You always start with a solid as a reactant, and it leads to products in solution. Okay, now here's the concept that we need to, actually, if we look back at equilibrium and our discussion of equilibrium constant, versus equilibrium position. You recall that they're not the same. Constant is a constant. If the temperature doesn't change, then that constant is exactly that, a constant. It doesn't change. But the equilibrium position can change depending on your starting point. If you start off with higher concentrations of reactants, then you should get more products. So that's a different equilibrium position. And if you invoke Le Chatelier's principle and you say add some product, then you're going to shift the equilibrium and you get a different equilibrium position, right? Okay, so along those lines, KSP is a constant for a given temperature, just like any constant is. Any equilibrium constant is constant. But that doesn't mean that the solubility of the product, of the solid, runs parallel to the Ks. If you compare 2 K values for different solids, just because one K value for one solid is higher than the K value for the other solid does not mean that the higher K value guarantees higher solubility. Well, what do we mean by solubility anyway? Well, if you have a solid and it produces, let's see, this would be minus and this would be plus, and these are in aqueous solution, right? The solubility is an expression of usually, well, there are a number of ways to express it, but the molar solubility will be how many moles of this solid will be in solution in, say, a liter of solution when it reaches equilibrium. Okay. Now you can express that in terms of mass if you want, and reference manuals will do that. If I want to find out the solubility of, oh, I don't know, calcium chloride, nah, it's very soluble. Let's use one that's less soluble. How about calcium phosphate? Then the reference manual will usually give that in terms of grams per 100 milliliters. That's typical. But that can be converted, right, to molar solubility. All you have to do is dimensional analysis. You convert the grams of the known compound to moles, and you convert the volume to liters, and you get molar solubility. So you can transition back and forth. All right, so the reason I shouldn't have erased that. The reason I'm focused on molar solubility is when we solve problems, the number of anions or cations may not be the same as the number of moles of solid that go into solution. So that just means when you do your solving your problem and you create unknowns, X values, for instance, then you have to choose them wisely. And I'll bring that topic up again in just a minute. Okay. So the point is that higher K value doesn't necessarily mean higher solubility. And for one reason, the solubility may be expressed in some units of measure, whereas the K value may be in different units. And the K value is usually determined by molarity concentration of the anions and cations, whereas the solubility might be in other units. But that's not the major difference between K and solubility. That the powers of your the coefficients that are used as powers will modify the K value tremendously, and that can influence the outcome of the calculation of solubility, which we're going to do in just a second. Oops, there we go. Okay, so let's say we're given the K value, the KSP, for silver chloride. We know that silver chloride is considered insoluble, but it does have a K value, which means what? It means that there are some silver ions in solution. There are some chloride ions in solution. Otherwise, you would not be able to calculate that value. As small as it is, there are still silver and chloride ions. Right? So how would we write that? Well, first of all, you got to write silver chloride correctly. Silver is a +1 ion, chloride is a -1 ion. Right? And it's a solid. It breaks up into these two ions like that. And the K value is 1.6 times 10 to the -10. Okay. So there we go. There we go. Oh, I didn't write the expression. So this would be simply that. The solubility product is equal. And since there are no coefficients, well, there are 1 and 1. So power of 1 and power of 1. Now, this slide skips steps. It goes straight to the X value, which is denoted as solubility. It calculates it. But how did it get there? Right? So I'm going to show you how it got there. You set up your ice table. Right? So you have nothing here for that because, right, it's a solid. It doesn't count. But initially, what do you have? We have nothing, right? When you first put silver chloride in solution, you have no silver and no chloride ions at all. Okay, so what happens at, what's the change toward equilibrium? Well, you're going to get one of these for every one of those. So if one of these goes into solution, then one of these shows up over here. Right? Now, the only reason I put that X there is so that we could draw a, we can make the connection between this X and that X. This X is going to be the solubility, right? That's how much you lose from this solid going into solution in terms of concentration, right? And this is how much is going to show up of these ions. So this was an easy choice for X, right? Because it's 1 to 1 to 1. So X is equal all the way across, except this one's negative and those are positive. All right, so what does that give us down here? Well, that's nothing, right? Because this is not part of the equilibrium. So you're going to have an X here and an X here. And then if you put an X in here, that's why you have X times X equals that value. X squared equals 1.6 times 10 to the minus 10. And X equals the square root of 1.6 times 10 to the minus 10. Okay, so that's where that comes from. And the solubility of silver chloride in pure water at standard temperature, which would be 25 degrees Celsius, is 1.3 times 10 to the minus 5 molar. Now, if you want to find out what that is in mass, you just interpret the value, right? 1.3 times 10 to the minus 5. Molar is what? Moles per liter. Moles of what? Moles of silver chloride per liter. Then all you have to do is say moles, grams, which is molar mass, correct? Find the molar mass of silver chloride and crunch the numbers. And you find out the, well, that's per liter, grams per liter. If you want grams per 100 grams, do a further conversion. All right. So that was fairly simple. And we choose simple to begin with. Silver chloride breaks apart into one ion each. One cation, one anion. So it's 1 to 1 to 1. That makes it very easy, very simple. But what if you've got a more complex ionic compound? Now what do you do? Well, let's change things. Right? Silver phosphate. You got to be able to write the compound, obviously. There's phosphate. It has a 3 minus charge, 1 plus charge. So that means you need 3 silvers, correct? All right. So now we got the compound. What ions does it produce? It still produces silver. Only how many silvers? If one of these goes into solution, you get 3 of those. Okay? And you get 1 of these. There you go. Now, what would the equilibrium expression be if the KSP is 1.8 times 10 to the minus 18, right? And notice the KSP for silver phosphate is less than the KSP for silver chloride, right? But we're going to find out what the solubility is. Is the solubility, in fact, for silver phosphate less than the solubility for silver chloride? Okay, so this expression would be what? Silver to the third power times phosphate to the first power. Okay? So now let's set up our ice table. All right. So in the beginning, of course, you have 0 here, 0 here. This one, if you lose one of these, that would be our solubility. How many of these do you get? Well, you get 1 phosphate, true. But how many silvers do you get? You get 3 X's. Okay? So now, that one doesn't matter. You get an X here, and you get a 3X here. Now, set that equal to the expression of 3X cubed times X. Okay? So this is equal to that. Let's see. Yeah, okay. So now that we got that, I need my space. So let me erase this. And let's say 1.8 times 10 to the minus 18 equals, what's this? Well, let's write it up here first. Yes, be consistent. There. Now, what's 3 cubed? 3 times 3 times 3 is 27, correct? 27. X cubed times X, which is 27x to the 4th. Okay? So, x to the 4th is going to be this number divided by 27. Right? So you pull out your calculator. 1.8 exponent 18 and divide by 27. I get 6.67 times 10 to the minus 20. Okay? So now what's x? X is the 4th root of this number. Now, how do you crunch that number in your calculator? Well, it depends. Some calculators do include the capability of doing higher roots than just square roots. Mine only allows for square roots. So I have to interpret this value mathematically in order to do my calculation. Mine will do infinite powers. So what I do is I set this equal to the power. So the 4th root of that number is the same as the 1/4 power. Right? I don't have time to prove it right now, but believe me, that is true. So I just take that number, enter it, and I do the 1/4 power, which would be 0.25. And I use my powers function in here, y to the x in my calculator. And then I put in 0.25 and I hit that button. And that's 1.61 times 10 to the minus 5. And that is the molar solubility of silver phosphate. Okay? Well, let's see, they rounded it off to 2. Is that accurate? Yeah, KSP is 2 significant figures, so I probably should round it off also. All right. So let's compare. we find that the KSP for silver phosphate is smaller. How about the solubility? Solubility for silver phosphate is actually larger, 1.6 versus 1.3 times 10 to the minus 5. I mean, that's not a big difference, but it makes the point. Just because the KSP is smaller doesn't mean the solubility is smaller. All right, any questions so far? Okay. So usually, if at all possible, you try to let the negative X in our ice table equal the solubility of the solid. That way, when you solve for X, you've got the solubility. There are some times when that doesn't work very well. Sometimes you need to let the X be something else. But that should be your starting point. Okay. Now, that was solubility in pure water. What if there's something else in there along with it? Right? What if the water is not pure? It's already a solution, and you try to dissolve your solid in it. Well, it depends on what's in there. And here we go back to the common ion effect. Right? Is there an ion in solution already that can be found in your solubility expression? So here's our example. We want to know, compare the solubility of silver chloride in water versus silver chloride in an acidic solution like nitric acid. So there's your solubility expression, but you've also got nitric acid in there. Right? So let's look at this. Silver chloride, most of that is going to be on the left-hand side. Right? It's heavily weighted toward reactant. Nitric acid, however, is heavily weighted toward product, H plus and NO3 minus, exclusively. So let's combine those two equations and see what we get. Right? So here's the reactants, silver chloride, nitric acid, and there's your products, silver ion, chloride ion, hydrogen ion, nitrate ion. Right? So how is the equilibrium going to be affected? Only if these ions interact in some way other than the starting materials. Right? So we don't say silver chloride because we already know how that reacts. How about silver and nitrate? Well, we find that silver nitrate is completely soluble. All nitrates are soluble. Right? According to the rules of solubility, but also if you look at the chart, you remember the chart, it's in your useful information. Silver nitrate is completely soluble, so there's nothing that's going to shift the equilibrium back toward silver chloride in that case. How about hydrogen ions and chloride ions? Right? Hydrochloric acid, it's a strong acid, it's completely soluble. So the addition of nitric acid to this picture has no influence whatsoever on the solubility of silver chloride. Okay? There are no common ions there to influence the solubility. Perhaps if you add, let's just suppose, instead of nitric acid, you add hydrochloric acid. What effect would that have? If you add extra chloride ions, what does Le Chatelier say? It says if you add extra chloride ions, you're going to shift the equilibrium back toward reactant. Right? So you would decrease the solubility if you acidified with hydrochloric acid. Okay, that's the common ion effect. All right, so I'm following along in my hard copy here. I want to see, be sure. Okay, now we're going to look at silver phosphate and how it behaves in solution. Okay, let's say instead of silver chloride, we have silver phosphate that we're trying to dissolve in solution. And we have nitric acid, just like the previous scenario. Will that affect the solubility of silver phosphate? We know it didn't affect silver chloride, but how would it affect silver? Silver phosphate? Well, nitric acid still breaks up into hydrogen ions and nitrate ions. And there are no common ions here, right? So we can't blame this one. If there's a difference, we can't blame it on common ion. There has to be something else involved if the solubility changes. All right, so what could change? Well, look at what you've got up here. If you're going to combine these two equations, think of cation-anion interactions. Silver nitrate again, completely soluble. How about hydrogens and phosphates? Right. Think about phosphoric acid. What does phosphoric acid do? Phosphoric acid, right, dissociates into one proton and HPO4 minus. And then that one also dissociates into one hydrogen. Remember, this was previous two chapters. H2, excuse me, H2, HPO4 2 minus, and then HPO4 2 minus dissociates into, there we go. So that's the sequence, and each one has a K value, remember? What do we know about those K values? As you step down, as each hydrogen is removed successively, the K values get smaller and smaller. That means they favor reactants. So what does that mean in terms of conjugate acid-base relationships? If this is a strong acid, that's going to be a weak base. But phosphoric acid is a weak acid. Right? It actually has a K value with a negative power of 10. This one's going to be even more negative power of 10, and this is going to be more. So as the acids get weaker, the bases get stronger. And this is a very, very strong Bronsted-Lowry base. It will latch onto a proton in a New York second. So that's what happens here. That phosphate picks up that proton and forms this ion. And based on the K values, I'm willing to bet that this species grabs another proton, and that species grabs another one. So what you're doing is removing phosphates from the product side. So if you look back up here, in this equilibrium expression, according to Le Chatelier, you're removing that product, which means the solubility is shifted to the right. So that should increase the solubility of silver phosphate. Right? This is just the first step, where you remove one hydrogen ion. But it will continue all the way up to phosphoric acid. Okay, so if the anion of the solid is a strong base, phosphate is a very strong base, then when you acidify the solution, you increase the solubility, always. So any other solid that is derived from a cation and an anion that's a very strong base, all you have to do is acidify the solution and you get more of it into solution. Okay? That's what drives the dissolution of silver phosphate and any other solid with a strong base as an anion. Okay. So let's actually calculate the solubility. Oh, no, it just says, sorry, I thought we were going to calculate. I didn't look at my hard copy. How does the KSP? Well, the KSP is going to be the same. The solubility does change. It's like the equilibrium position changes because we invoked Le Chatelier. But the KSP does not change. Okay? You still got this reaction in solution, and it has its KSP. Now, you could calculate a K value for this reaction, right? That's possible. You just need a K value for this one, which might be hard to come by, but it should be doable. It would be a very large number, obviously. But the K is a constant. It does not change unless the temperature changes. But the solubility did change. All right. So let me see. Right. So now, let's make some room. And my board's walking again. Okay. Let's actually calculate the solubility of silver chloride in a solution that already has some chloride ions in it. This solution is made up of 4 times 10 to the minus third molar calcium chloride. That's a very small amount of calcium chloride in solution. So we could speculate, you know, we might say, well, that's not going to have much influence. I mean, there's not much there, right? Well, let's just see. Since chloride is a common ion here, it's going to influence the solubility of silver chloride. So we need our ice table, right? I left out the silver chloride. The silver chloride over here would determine what your X is. So the X is in terms of silver chloride, and since they're 1 to 1 to 1, plus X here, plus X there. The difference is you're starting off with some chloride. Right? Before we had nothing, 0 and 0. But here you're starting off with a little chloride. How much chloride? Well, notice that the concentration of calcium chloride is 4 times 10 to the minus third molar. But there are 2 chlorides for every calcium chloride. That means chloride ions are actually 8 times 10 to the minus third molar. Okay, so that goes into the equilibrium expression here. So there's your solubility product, and there's the unknown expression. Right, this one times the chloride. Well, here's where we have to decide: is X large enough to be considered in this reaction? If we do keep X, that means we get this term times X, and this term times X is squared. So now we have a quadratic equation, which requires that messy formula. But can we ignore this x right here? Is this x going to be so small that it doesn't matter? Well, we have to look at the KSP, right? The KSP says even in pure water, x is going to be extremely small. In fact, we determined that the x was 10 to the minus 5, right? And even if it was that soluble, it would still be insignificant compared to 10 to the minus 3. Okay, so we can ignore x. So that's why we say it's approximately equal to this term. That simplifies things. Oh, excuse me. Okay, now we just solve for the unknown. X now is this value divided by that value, which is 2 times 10 to the minus 8. And all you have to do is plug that number back into the expression and see if it gives you roughly, or very close to, within 5% of this value. And it should, right? Because you know, if that value is 10 to the minus 8, it's not going to have any influence at all on 10 to the minus 3rd. All right, so the solubility in this environment, specific to that concentration of calcium chloride, right? If we change that concentration, we change the solubility. We change the equilibrium position. So we compare that 2 times 10 to the minus 8 versus 10 to the minus 5, right, from our previous calculation. So we have decreased the concentration of silver chloride by trying to dissolve it in a solution of calcium chloride. Now, how could that be used in a practical application? Well, suppose you've got a reaction which produces silver chloride as a product. You want to be sure that you get all of that silver chloride out of solution. You don't want to leave anything in solution, or you want to make it just the barest minimum possible. All you have to do is, once the reaction is complete, assuming compatibility is taken into account, is add a chloride salt to the solution. That will further decrease the solubility of silver chloride and drive anything that's left in solution into the solid phase. And then you can filter it, and you can be fairly confident that your recovery is quantitative. All right. Now, why didn't we care about 100 milliliters? Because we were already given the concentration, right? And the addition of silver chloride solid didn't change the concentration at all. Didn't change the volume either, because none of it's in solution. Well, very small amount, of course. But the 100 milliliters was not needed. Sometimes it is needed. Depends on the problem, the way it's stated. But in this case, we didn't need it. Pardon me. I had a cat trying to crawl into a bag. That's a recipe for disaster. Okay. How about silver chloride solubility in calcium nitrate? Here we look for a common ion, right? Are there any ions in there that will affect the equilibrium expression for silver chloride? No. Right? There's no nitrate there. There's no calcium there. This solution concentration, doesn't matter what the concentration is, it has no influence whatsoever on the solubility of silver chloride. Right? So we end up with the same solubility as before. Okay. Now here's another problem. Suppose you have a solution, for argument's sake, there are 2 ions in that solution that you want to precipitate. Well, okay, the way this problem is stated, pardon me. You're going to mix a solution of cations and a solution of anions. And you know that when you put them together, there's the possibility that they will form a solid. How do you know if they will form a solid or not? You have to resort to the Q, right? Calculate the Q. So let's use silver chloride as an example. I'm going to leave out the aqueous just for simplicity. And the Q then would be calculated the same way as the K. All right. So we compare the Q to the K. Actually, I wrote that wrong. Let's go ahead and do it this way. Rather than erase my square brackets, that's the K. The Q is this. In parentheses, because that's not at equilibrium. Okay, so we compare them. So what if they're equal? Well, if they're equal, you're at equilibrium already, right? And if you put those two together and these are equal, then you can assume that nothing's going to happen, right? You've already got these in solution. There's just no solid left. You're right at that stoichiometric point. So they won't form a solid. Well, what if you go one way or the other, right? Say Q is greater than K. What does that mean? That means that these concentrations are greater. The product of this one is greater than the product of that one. So that means if you increase one of these, then it's going to form a solid. So when Q is greater than K, you will precipitate some solid. But if Q is less than K, that means you don't have enough. The concentration is not high enough to meet the conditions of this K, and they will just sit there in solution and do nothing. No precipitation. Okay, so we can use that information to selectively precipitate ions that are in a mixture. We call it selective precipitation. So if you have a mixture of metal ions in solution, you need to pick the addition of an anion such that a precipitate could form and be selective, right? Will it form a precipitate with only one of the metals? That would be ideal. Then you could remove that metal selectively. But what usually happens is you add an anion that will precipitate more than one of them, but not all of them. So you separate them into groups, and then you have to further treat them to separate those ions. But for argument's sake, let's say we only have two. In this case, we have barium, 2+, and silver ions in solution. So in order to get them separated, we say, all right, what could I add to that solution that would remove silver but not touch barium? If you added chloride ions, that might do it. Chloride ions will react After you reach a certain level of chloride, right, your Q exceeds the K and you start to precipitate silver chloride. So you add chloride ions. Will chloride ions precipitate barium? No. Remember, most chlorides are soluble. There are only a few, three or four, that will precipitate with chloride. So that would be a good choice. You want to add chloride as the acid. Now, why would I choose HCl and not some other chloride like potassium chloride or sodium chloride? Well, it's purely practical consideration. If you add chloride in this form, what else do you have in there? Well, you have hydrogen ions, right? And they're just going to react with water, right? They'll make the solution more acidic, but they won't be an interferent for the recovery of barium. If we added sodium chloride or potassium chloride, then we would have removed silver chloride, but now we've got a solution of barium contaminated with sodium or potassium. Then you got to, how do you get those separated? If you use HCl, now you've got the silver chloride separated and there's no interference. All you have to do to get the barium out is either precipitate it with some other anion or just evaporate it, and you've got barium left. Probably as the chloride, barium chloride. But the barium chloride will not form until you remove all the water. Okay, so that's how I would separate silver ions from barium ions in this situation. Now, how do we know barium and silver are in there in the first place? Right? If we didn't put them in there, you need some way to analyze to prove that they're in there. Years ago, wet chemistry would have been a tedious practice, taking at least a day to determine qualitatively what's in solution. Nowadays, we have quicker means. They're expensive, but they are quicker. I used to operate an instrument called an inductively coupled argon plasma spectrometer, which is a fancy name for a hot torch. You pump your sample into it. It's so hot, 10,000 K, breaks everything apart and excites all your metals. And then you focus your optics on the part of the flame when they start to cool down. And then they emit light. And you pick up that light, run it through your spectrometer, spread it apart, and they have characteristic wavelengths for each element. And you can say, all right, that one's there, that one's there, that one's there. So that's a qualitative determination. That instrument will also do quantitative if you calibrate it for different concentrations. There are cheaper ways. Let's see. There are ways to modify other instruments to do that. But if you've got, $150,000, you can do it with an argon plasma. Okay, let's say we have a more complicated mixture. Now we have copper 2+, mercury 2+, nickel 2+, and manganese 2+. The charges are important because the solids that form, especially with transition metals, the solids that form are dependent upon the charge of the cation. You form a different solid with a different charged cation. So manganese 4+ would form a different compound, which may be soluble, may or may not be soluble. I don't know. But let's say we have all these 2+ ions in here, and we're proposing the use of hydrogen sulfide to remove them. First question is, what's going to react with them? Well, the hydrogen's not. The sulfide is our anion. So the anion would react with these, perhaps. So we just look for, does the sulfide form a solid with each one of these? Well, the answer is yes. It will at a certain point. So we just need to know what is the certain point. If we're going to separate them, we need to know the K values for each of the sulfides of these. So if you find that the K values for one or more of these is very, 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 very low, then your best bet is to reduce the sulfide concentration to the point where it will not precipitate the others, but is sufficiently high for the Q to exceed the K. And that's what we do first. We put hydrogen sulfide in solution. It's soluble, but we want to minimize the concentration of sulfide ions, right? So we, let's see, did I put that in there? Yes, I did put it in the slide. So here's the hydrogen sulfide equilibrium with hydrogen ion and hydrogen sulfide ion, HS minus ion. Notice that this is an acid dissociation, right? H2S is a weak acid, right? So it will form HS minus, and then HS minus will decompose into H and S2 minus. That's the species that we're looking for, but we want it to be low concentration. So we acidify the solution. Now you acidify the solution based upon calculation, or usually based on recipe. And notice that when we combine these two equations together so that we are focused on S2 minus, the overall K is this one times that one, which is 10 to the minus 20. Right? So if we convert the sulfide, or if we put the sulfide in solution, then all we have to do, this K is constant, but the equilibrium position, we want to shift toward the H2S to decrease the sulfide concentration. So we just add more acid in some form, right? Usually chloride, because all of these chlorides, well, let's see. No, chloride wouldn't be possible because mercury 2 plus, mercury 2 chloride is insoluble. So we would have to choose a different one, like nitric acid. That would be a good one. Choose nitric. Then you would add hydrogen ions here, and the nitrate would just still be a spectator. Okay. Now, what does that low level of sulfide do? It precipitates mercury and copper because their Ks are very, very low. Then we want to precipitate nickel and manganese. Get them out of solution. So how do you do that? Well, you need to remove some of those hydrogen ions, right? So if we combine if we have this situation, H2S yields 2 hydrogens plus sulfide. Before, we added hydrogens and shifted the equilibrium back this way. Now, if we add hydroxyls, we remove hydrogens, right? Remember, the equilibrium for water dissociation is way towards water. That means hydroxide is a strong, very strong base. So it will take those hydrogens and make them into water. And that shifts the equilibrium back, and now we're producing more sulfide. That way, you increase the sulfide concentration to the point that it will precipitate nickel and manganese. That's how you separate these two, this group from that group. Now you've got copper and mercury together in the same solid. You have to do further processing to get them apart. But that's beyond this course. All right. So this is what it would look like in a flow chart. All right, you have this solution. If you add H2S that's been acidified to a pH of about 2, that's sufficient to guarantee copper and mercury precipitation without precipitating manganese and nickel. And then you basify, you add hydroxyls and increase the pH to around 8. Then that allows for the precipitation of manganese sulfide and nickel sulfide. Right? That's just one tiny application of the knowledge of equilibrium of these solids, the solubility products, and how you would use that to separate a mixture of metals. But it gets even bigger than that. So that's what this is. For this situation, you have a mixture of all of these metals. Right? And this is fairly representative of what you would find in a mixture, or you could find in a mixture. So notice that we've got lots of 2 pluses and 3 pluses. Okay, there's our silver. Notice we have 2 forms of mercury. This mercury 2 plus and that mercury 2 plus. Notice, remember that mercury is kind of freaky that way. Mercury always has a 2 plus charge. But sometimes when it has a 2 plus charge, there are actually 2 mercuries there. So in this case, that one would be an oxidation state of 2 plus. This one would be an oxidation state of 1 plus, because there are 2 splitting that 2 plus. Okay, so those 2 types of mercuries will behave differently in this precipitation flow chart. All right, so what do we do first? Well, the simplest thing to do is acidify the solution, because anything that is forms an insoluble chloride, and there are just a few of them that do that. Silver, this mercury 1 plus, and lead will precipitate with HCl. So you add hydrochloric acid, and that gives you what we call group 1, insoluble chlorides. Right? You don't have to memorize this chart, in case you're wondering. It is contained in useful information, both in the review document and in the same folder where your exam is located. And remember, you have to print out those useful information documents before you go into lockdown browser. Right? You probably know from experience that once you get into lockdown, it won't let you look at anything but the exam. So be sure and print these out first. Go into that folder in your browser, your regular browser. Print the documents, then go into lockdown, and you'll have the documents there with you. And if I see you looking over at something like that, I know you're looking at those documents. Okay, so that's group 1, the insoluble chlorides. Now what? Well, it's already acidified, so just add some H2S, right? So how would we acidify it? How far would we acidify it? Around pH 2 should be enough, right? That's fairly high chloride concentration. We found that you can drop silver chloride out of solution to an extra 3 orders of magnitude. Yeah, maybe it was 4. No, it was 2 orders of magnitude. 10 to the minus 3rd, 10 to the minus 5. Anyway, this pH is probably around 2. So then you add your hydrogen sulfide and you precipitate the insoluble sulfides. Right? Now, we looked at just a couple of them before, but there are a lot of them actually. There's this mercury 2, will precipitate as the sulfide, and there's your copper also. But bismuth, cadmium, lead, arsenic, antimony, tin, they'll all precipitate as sulfides. And that's your group 2. Okay, then what do? Well, then you neutralize it, right? You bring the sulfide concentration way up. These are the acid-insoluble sulfides. Then you increase the pH to 8 by adding sodium hydroxide. And now you get the, actually you get a combination. You get the base insoluble sulfides, plus you pick up those insoluble hydroxides. Right? So you get the zinc sulfide, nickel, cobalt, manganese, iron out of that group. Right? And you also get aluminum hydroxide, iron hydroxide, and chromium hydroxide. These are the group 3 precipitates. Now, what's the group 4? Well, now you add, since you're already basic, then you add some sodium carbonate, which would itself form basic solution, but it just adds carbonate. And then you precipitate the carbonates, barium carbonate, calcium carbonate, magnesium carbonate. And then what do you have left over? Well, anything that's left over has to be soluble in solution, and you get it out by evaporation. And it looks like the only thing out of this group that we have left now is ammonia. Now, this scenario was chosen because these cations are the most common that you would find in a mixed solution of cations. There may not all of them be there. And you can determine that, of course, right? Like I said, all you need is an expensive piece of equipment, and you can quantitatively, you can do it benchtop also. It just takes longer and it's more tedious, but you can do qualitative tests. And in fact, when I was going to, as an undergraduate, some colleges offered chemistry in 2 forms: qualitative chemistry, quantitative chemistry. Where I went to school, we didn't do it that way, but it used to happen that way. And they would teach you how to qualitatively assess a sample for its components. That would probably be a good course to take if you were going to be going to forensics. Because when you get a sample in a forensic lab, I mean, you have the barest information. Maybe you know it's a body fluid, maybe you know it's a water sample, maybe you know it's scraped off somebody's boot or a boot print in the, you know, so something like that might come in handy. And you can find a college that teaches a course in qualitative analysis. Okay, so that was, that's up to this slide is all about solubility. And let's see, we got lots of time left, don't we? I'm good until noon. I've only used up about an hour and a quarter. Okay, so we're probably gonna finish this one ahead of time. So now, remember, we mentioned that one way to increase the solubility of an insoluble compound is to find a way to remove the anion. And our example was silver phosphate. Right? All we had to do is find a way to remove the anion, and we get the silver phosphate into solution. And we did it by acidifying. right? If you add acid, then this strong base will latch onto that proton and remove it from that equilibrium. Okay, that's one way. If you don't have that opportunity, if the anion is not a strong base, then we need to focus on the cation. Can we put the cation in solution in some way to increase the solubility, right? And the answer to that is yes. And the way we do it is we form a complex ion. All right, so what's a complex ion? Well, a complex ion starts with a metal ion. And for all intents and purposes, the metal ions we're concerned with are transition metals. All these guys right in here. Now, sometimes these metals also get into the act. So it's transitions plus. And even you can form complex ions with some of these lanthanides and actinides, but we're not gonna mess with those. It's just beyond the scope of this course. To teach this concept, we're going to focus on transition metals. So you have a metal ion, and the metal ion, whatever charge it may be, I'm just using 1+ here, associates itself with, now here we're going to go back to the concept of Lewis acid and Lewis base. Remember? So let's say a Lewis base is what? Lewis base is an electron pair, what? Donor. And a Lewis acid is an electron pair acceptor. Okay, so we've got Lewis acid base chemistry going on here. So we've got this is a metal. So what's it likely to be? It's likely to be an acceptor, a Lewis acid. So this Lewis acid associates itself with one or more ligands. And these ligands are groups that behave as Lewis bases. And they usually have at least one lone pair to donate. Right? That's what makes them a Lewis base. They can donate a pair, and they form a bond. Right? So what kind of bond is that? Remember? When normally in a covalent bond, you get one electron from one side and one electron from the other. If both electrons come from one side, that's a coordinate covalent bond. So you get that bond. And this may be charged. It doesn't have to be charged. It only needs the pair of electrons to donate. So if it's charged, then you do a charge balance for the whole ion. In this case, the whole ion would still be positive. But there could be another one come in here, like this, and also form a bond. Right? You're not limited to 1, 2, or 3. In fact, the most common, coordination number, they call it. The most common coordination number for complex ions is 6, followed by a close second with 4, most of them. Now, the one we're using as an example only has 2, the silver complex ion. Okay, I'll leave that there for the second. Okay, so this ligand is a Lewis base, and the reaction of the metal with the Lewis base to produce a complex ion has an equilibrium constant associated with it. And in fact, it behaves similarly to acid dissociation. Remember, when an acid dissociates, each step, losing one proton at a time, each step has a K value. Well, as you add ligands to your metal, each one of those additions, one at a time, has a K value. So here's an example. We're going to form a complex ion between beryllium 2+ and fluoride ion. And each addition of a fluoride, right, gives you a complex ion with a K value. But we determine by analysis that the addition of fluorides doesn't stop until you get to 4 of them. 4 fluorides and beryllium is the final step. So we find that the equilibrium constant for this one, right, and that K down there probably should be like this, KF for formation. So notice the K here is extremely large, and because all of these components are aqueous, every one of them is part of the equilibrium expression. So the first equilibrium expression there would be, that would be the first one, would be this one, divided by this one. Yep. Times this one. Okay. And that would be heavily weighted toward the formation of the complex ion. This one. Way to the right-hand side. 7.9 times 10,000. 10 to the 4th. So you know that predominantly it's going to be this one. And then this one picks up another fluoride. And its equilibrium is very large too. Right? 5,800. 5.8 times 10 to the 3rd. So its equilibrium is going to be way to the right. So what does that mean? Well, if this equilibrium is way to the right, and it's depending on this reaction to supply beryllium fluoride +1 charge, then whenever this one is formed, this one picks it up. So that means most of that is gone. And this one forms that ion. It becomes the reactant for this reaction. It's very high K, and this one's also a very high K before it stops at BeF4 2-. Now, each one of these complex ions has a name, right? But we don't have time to go into that. I've got a document that will help you if you ever want to review nomenclature for these ions. I've got a document, it's in Blackboard. Nomenclature of coordination complexes. And it gives you the rules in very short, compact form, logical form, and you can name them. For instance, this is an anion. All right, so I would name this one as, you start with the ligands. This one would be tetrafluoro. Am I right? Yes. Tetrafluoro. Berylliate. Tetrafluoroberylliate 2. Let's see, is that right? Yes. Roman numeral 2. Roman numeral 2 in this case does not refer to the metal, it refers to the whole ion. Right? So it can get pretty complicated, and we don't have time to deal with it. In fact, I've just wasted 3 or 4 minutes telling you about it. Okay, so overall, what would be the formation of this complex ion? Well, you know how you do that. You add all of these together and cross out the terms that are on both sides of the arrows, and the composite equation is 1 beryllium combines with 4 fluorides to make this ion. And the K then would be each one of these times that one, times that one, times that one, times that one. Right? 10 to the 12th overall, which means, I mean, what's 10 to the 12th? It's, let's see, gigatera. It's in the tera region. So for all intents and purposes, all of that beryllium is picked up and shifted over to this side. Now, of course, that's not to say the equilibrium position is over there. Depending on your starting concentrations, you may still have some beryllium ions in solution, but any beryllium solid will more than likely be solubilized. All right, so that's an example of complex ion equilibrium. Now, the 2 strategies I've already mentioned, right? If you have a solid and the anion is a strong base, just acidify the solution, and you will increase its solubility. If you acidify it enough, you get everything in the solution. But if you don't have a strong base, focus on the cation, form a complex ion, right? So in this case, we need to form a complex ion with the silver ion. And I've got a video, next, a video from Khan Academy that works through all of it, actually. It goes back and it looks at the equilibrium of silver chloride, and then it looks at the complex ion. So there's going to be some repetition, but I think it's valuable. It's a long video. It's like 14 minutes. But it does do a lot of the heavy lifting for me in the subsequent slides. And then when I talk about the slides after this video, then I can add some embellishment to it. So here's the video. You may have to turn up your volume because I think the volume didn't come through very well.
First, let's calculate the molar solubility of silver chloride in pure water, and then we're going to compare the solubility that we'll get in part A to the solubility that we're going to get in part B. And in part B, it's no longer pure water. We're going to have some ammonia present. So we take some solid silver chloride, so that's this over here, and we put it in some pure water. And some of the silver chloride is going to dissolve, but most of it's going to stay in the solid form. So silver chloride is only a slightly soluble compound. So there's my little pile of undissolved silver chloride. But some of it does dissolve, and so we get a saturated solution of silver chloride. So there are silver +1 cations in solution, and there are also chloride anions in solution. And we have our solubility equilibrium. To find the molar solubility of silver chloride, let's go ahead and write down our ice table. So our initial concentrations, our change, and finally our equilibrium concentrations. Before we put the silver chloride in, we didn't have any ions in solution. So the initial concentrations of our product are 0, right? We have 0 for the concentration of our ions. Some of the silver chloride that we put in dissolved. So we lost a certain concentration of our silver chloride, and we're going to call that X. So we're losing a certain concentration of our silver chloride. If we look at our mole ratios, for every 1 mole of silver chloride that dissolves, we get 1 mole of silver +1 cations in solution. So if we're losing X over here, we're gaining X. We're gaining X for the concentration of silver cations in solution. And since our mole ratios are still 1 to 1, if we dissolve 1 mole of silver chloride, we gain 1 mole of chloride anion. So over here we get a plus X. So at equilibrium, our concentration of silver cations is X, and our concentration of chloride anions is X. So we write our equilibrium expression, and since this is a solubility equilibrium, we're going to write KSP, our solubility product constant, is equal to concentration of our product, so that's concentration of Ag plus, raised to the power of the coefficient, so raised to the first power, times the concentration of chloride anions, Cl minus, raised to the power of the coefficient to the first power. So we can plug in our solubility product constant at 25 degrees. It's 1.8 times 10 to the negative 10. So we put in here 1.8 times 10 to the negative 10. And this is equal to, this would be X times X. So this is equal to X squared. So we can get out the calculator and solve for X. So we have the square root of 1.8 times 10 negative 10. So take the square root of that, and X is equal to 1.3 times 10 to the negative 5 if you round that. So X is equal to 1.3 times 10 to the negative 5 molar. So that's the concentration of, let's say, our silver plus 1 cations in solution. That's also the molar solubility of silver chloride, right? That's how much we can dissolve. So not very, it's a very small molar solubility. So silver chloride is only a slightly soluble compound. Let's see what happens when we have ammonia present instead of pure water. So we have a 3 molar, right? We have some ammonia present. Now, what happens when ammonia is around silver cations, right? We get this reaction. So silver cations plus 2 molecules of ammonia give us what's called a complex ion over here. And let's show what's happening. So if we have a silver plus 1 cation, right, we have 2 molecules of ammonia. So let me go ahead and draw in my 2 molecules of ammonia. And this is certainly not drawn to scale. So I'll draw 1 in on that side. I'll draw another 1 in on this side. Remember your definitions for Lewis acid, Lewis base, right? A Lewis base is an electron pair donor. And that's what's going to happen here. The nitrogen has a lone pair of electrons, and each ammonia molecule is going to donate a pair of electrons to our silver plus 1 cation. Right? So ammonia is donating as an electron pair donor, so this must be our Lewis base. And the silver plus 1 cation is accepting a pair of electrons, so this must be our Lewis acid. So the formation of a complex ion is a Lewis acid-base reaction. And notice the equilibrium constant for this, 1.6 times 10 to the 7th. Kf is called the formation constant. This is a very high value for the equilibrium constant, right? So the equilibrium lies to the right, and this is a stable complex ion. So any silver ions that are in solution, if you have ammonia present, ammonia is going to pick up that silver ion and essentially remove the silver ions from solution. So if we go back up here and think about our equilibrium, right, if we have ammonia present, we're going to be removing silver cations from solution, right? So we're decreasing the concentration of silver cations. We're decreasing the concentration of one of our products. And Le Chatelier's principle says if we're decreasing the concentration of one of our products, our equilibrium is going to shift to the right to make more. Therefore, increasing the solubility of silver chloride. More is going to dissolve because the ammonia is present, because of the formation of our complex ion. So if we added some ammonia, right, if we add a solution of ammonia here, we could get our silver chloride to dissolve, right, because it's more soluble because of the formation of a complex ion. So let's say we add enough ammonia solution where we get our silver chloride to dissolve here. So that's the idea. Adding our ammonia, right, caused formation of a complex ion, which increased the solubility of our silver chloride. So we would expect an increased solubility here of our slightly soluble ionic compound, silver chloride. And next, we're going to do the calculation. We're going to find the solubility of silver chloride in our 3 molar ammonia solution. Now we've looked at 2 reactions. We've looked at the solubility equilibrium for our slightly soluble compound. And we've also looked at the formation of our complex ion. Now let's add those 2 reactions together to get our net reaction for what's happening. Right? So we're going to add our 2 reactions together to get a net reaction for what happens when you put silver chloride in ammonia. Right, we have silver cations on our reactant side and on our product side, so we can take those out. And so for our reactants, for our net reaction, we have solid silver chloride plus ammonia. And for our product side, we would have our complex ion and our chloride anion. So we have our complex ion, and we also have chloride anions, so Cl-. So that's the net reaction. And if we added those 2 reactions together to get our net reaction, we have a new equilibrium constant, which I will call K. And if you add 2 reactions together to get your new equilibrium constant, you multiply the equilibrium constants of those 2 reactions. So K is equal to KSP times KF. So if you did that calculation, 1.8 times 10 to the negative 10 times 1.6 times 10 to the 7th, you'll get your new equilibrium constant. And I won't do it here just to save some time, but if you do that, you'll get 2.9 times 10 to the negative 3rd. So that's a 9, 2.9. All right, our goal is to find the molar solubility of silver chloride in our ammonia. So we set up our ice table, so our initial concentrations, our change, and then our equilibrium concentrations. And let's pretend like we're starting out with our solution of ammonia and we haven't added any silver chloride yet. Let's go back up here and let's see what our concentration was. Well, we started with a 3 molar solution of ammonia. So let me put that down here. So our initial concentration for ammonia is 3 molar. And if we haven't added any of our silver chloride, then we don't have any of our complex ions. The initial concentration of our complex ion is 0. And we also wouldn't have any of our chloride anion either, so that concentration would be 0 too. So now we add our silver chloride to our solution of ammonia, and some of our silver chloride is going to dissolve, and so we make that concentration X. So we're losing a certain concentration of silver chloride, so we write minus X. Next, we look at our mole ratios. So the mole ratio of solid silver chloride to ammonia is 1 to 2. So for every 1 mole of silver chloride that dissolves, right, we're also going to lose 2 moles of ammonia. So we write minus 2x here. For our products, if 1 mole of silver chloride dissolves, we make 1 mole of our complex ion. Right? So if we're losing x over here, we'd be gaining x over here for the concentration of our complex ion. And same thing for the chloride anion, because our coefficient is a 1. So we're going to gain x for the concentration of chloride anion. So at equilibrium, our concentration of ammonia is 3 minus 2x. Our concentration of complex ion is x, and our concentration of chloride anion is also x. Next, we write our equilibrium expression. So K is equal to concentration of products over reactants. So I look at my complex ion over here, so concentration of our complex ion, and we raise the concentration to the power of the coefficient, so to the 1st power. This is times the concentration of our chloride anion, so times the concentration of chloride anion raised to the power of the coefficient, so raised to the 1st power. We also have some reactants here, so we leave silver chloride out because that's a solid, right? But we have ammonia, so this is all over the concentration of our reactant, so this is over the concentration of ammonia. And notice our coefficient is a 2, so we need to have a 2 here. Next, we plug in our equilibrium concentrations. So our equilibrium concentration of ammonia is 3 minus 2x, our equilibrium concentration of complex ion is x, and our equilibrium concentration of chloride anion is x. So on the right side, we would have x to the 1st power times x to the, let me take that out, times x to the first power, right, all over 3 minus 2x to the second power, so squared. And then we can plug in our equilibrium constant k, which is 2.9 times 10 to the negative third. So 2.9 times 10 to the negative 3 is equal to, on the right side, we would have x squared. So we write this out. We would have x squared over 3 minus 2x squared is equal to 2.9 times 10 to the negative third. And so what we could do here, these are both x squared, right? These are both x squared, so we could just say that this is all squared on the right side. And then we can take the square root of both sides, right? So take the square root of 2.9 times 10 to the negative third, and take the square root of what's on the right. So the square root of what's on the right would be x over 3 minus 2x. And let's take out the calculator to do the other one. So square root of 2.9 times 10 to the negative third is equal to, let's round that to 0.054. So it just makes it easier here to round that. So 0.054. Our goal is to solve for x. Our goal is to solve for the molar solubility. So we can multiply both sides by 3 minus 2x. So when we do that, right, we would have this. So we need to multiply 0.054 by 3. And if you round that, you're going to get about 0.16. And 0.054 times 2 is approximately 0.11. So we have 0.16 minus 0.11x is equal to x. So we have 0.16 is equal to, we put both x's on one side. This is 1x, and this is 0.11x. So 1x plus 0.11x is 1.11x. And so now we need to solve for x. Right? So we've done our math here. So we have 0.16, and you divide that by 1.11, and that is equal to 0.14. So x is equal to 0.14, which is only approximate because of all the rounding that we've done. So this is concentration. Right? So this is our molar solubility. If we go back up here, x equal to 0.14 molar. Right? So that's our concentration of complex ion in solution at equilibrium. That's our molar solubility of silver chloride. Right? So it's 0.14 molar. Let's go way back up to the beginning and compare the molar solubilities. Right? So in pure water, the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar, which isn't very soluble at all. But now we have ammonia present. We've increased the solubility, and we just calculated the molar solubility is 0.14 molar. And obviously 0.14 molar is a lot larger than 1.3 times 10 to the negative 5. So the formation of a complex ion increased the solubility of our slightly soluble compound, silver chloride.
All right. That was Sal Khan doing a pretty good job of explaining all that. Here we go. Okay. So when we're looking at the formation of the complex ion with silver and ammonia, what are the species that are involved in this reaction? Notice that in my representation here, I've taken the formation of the complex ion and split it into 2 steps, which is the way it really happens. Now this one we already knew. These 2 are the K values for the first acid-base reaction, Lewis acid-base reaction, and this one's for the second Lewis acid-base reaction. What Sal Khan did was combine these 2 into a value, and that's where our differences are going to be. When I show you the subsequent calculations, they're going to be a little bit different than his, simply because he used a composite value here, and we didn't know where it came from. We assume it came from this multiplication of K1 and K2. but I'm going to use them separately. Okay. The next point I want to make is the complex ion formation lies very far to the right, and that was also something that Saul Kahn said. That means virtually all of the silver ions produced from silver chloride dissolution are converted to the ammonia complex of silver that we can infer from the equilibrium constants. So whenever you get a silver here, it's picked up by an ammonia here. Right? So, which means everything is in solution together. So a composite reaction would be valid. We just combine the three. Now, I want to stop for just a minute. What's required? In order for this complex ion to form, you've got to have ammonia in solution, NH3. And for the longest time, I assumed that this reaction was essentially to the right, where ammonia and water combine to make ammonium hydroxide. The fact of the matter is that this reaction also has an equilibrium constant. And the question is, which way is it? Well, the lab that you're going to do to determine the solubility product, or actually the formation constant for this reaction, the composite K value for that reaction is the complex ion lab. And in that document, I've added an appendix. I've added an appendix that explains why, or actually calculates the amount of ammonia in solution. And as it turns out, there's over 99%, based on that calculation, over 99% of this is ammonia in solution when it forms the complex ion with silver. So, and that's at 1 molar. I did the calculation. So at 2 molar, the dissociation would be less. Remember our discussion of acid dissociation based on concentration. If you increase the concentration of your acid, you decrease the percent dissociation. It's the other way around. If you decrease the concentration, we went from 3, which was Saul Kahn's concentration, to 1 molar, which is the one we use in the lab, the dissociation would increase. But I've calculated it to be greater than 99% ammonia. So if you go to 3 molar, you're going to even have a higher percentage of the compound in the form of ammonia. Okay, so there's what happens when you combine the reactions. You get this reaction, and here's the K value, right? And we've already canceled the common terms from both sides of the equation. So I think what was Saul Kahn's value? He used 2.9, I believe. Now I get 2.75. So there's slight difference. And the reason for that is I used these original values for my combination, and he used a composite. So there was already a rounding error built into his value when he did the further rounding. So I think mine is more accurate. I'll go with that. Okay, so here's the expression just like Saul gave it to you. And the other point I want to make is, notice the overall KEQ, the K value, is negative, right? So if you just focus on this equation, that says that most of this is over here in an equilibrium scenario. The way you talk about it, in terms of equilibrium. Equilibrium is way over here, right? But we have very high concentrations of ammonia. 1 molar in your lab experiment, 3 molar in Sol Khan's example, and that's why we have very large concentrations of ammonia, so that we drive the reaction to the right. And the concentration of ammonia in solution after the reaction is still very high. All right, so here's our overall reaction. This is what it would be if we used 10 molar ammonia. So we do the same type of calculation, right? We just substitute in here, instead of 3, we substitute 10. And we do our calculation for solubility. And we find out that the solubility now, instead of, was it 0.14? Instead of 0.14 now, the solubility is 0.47. So we've increased the solubility 4 times by going from 3 to 10 molar. Also, you can calculate how much ammonia is left. Right? So in this case, we've used about 10% of the ammonia. Right now we've got 9 molar instead of 10 molar. But there's still a huge amount of ammonia still in solution. Now that value for the ligand depends upon the individual reaction. The individual complex ion formation reaction will determine basically how much of the ligand you need in solution to facilitate the dissolution of your solid. In the case of ammonia and silver, this is what's required. Okay, I think that's the last slide, actually. Yep, that's the end. So we'll stop the share, and we're an hour ahead of time. So this topic didn't take a lot. I thought it would take a little longer, but things ran smoothly. And we've got extra time if you need to voice any opinions or talk about anything special. I'll still have the lab session at noon if you want to come talk about it, but we can talk about labs now if you want, since we've covered everything that I want to cover. So next week we'll have a review on chapter 16, and I encourage you to take that review document on chapter 16 that's in Blackboard, and work those problems that will give you experience working these types of problems. And anything that you can't work on your own, go to the worked problems document that's companion, and see if you can find out where your mistakes are and smooth it out and feel comfortable with it. And anything that you can't deal with in that way, bring it to class on Monday, and we'll tackle those problems first before we get into anything else. Nobody as yet has done that to a significant degree, but I can't help but believe that there are issues that you're just not bringing up. If you don't bring them up, I can't help you with them. I don't solve generalities. I solve specific problems. So if a student comes to me and says, Dr. Blythe, I don't understand, I can't help you. You need to be specific. What don't you understand? Then we can tackle the problem. Okay. Any comments? or questions that need to be covered? I'll give you, add an extra hour to your day that you don't have to be in class, unless we have some topics to cover. Let's see, we only have, what do we have left? Electrochemistry, I think, is the last one. Oh, no. No, we've got two things. We've got two things. Ooh, about to forget a big topic. Entropy comes next, and then electrochemistry. Okay. All right. Well, nobody has any issues. We'll call it a day, and I'll be back at noon in case you have any lab questions.